Hi everyone, welcome back to Chem Help ASAP. In this problem set video, we are going to be focusing on stoichiometry. But first we will start with chemical equations, identifying parts of chemical equations and balancing chemical equations. Then we will move on to the mole ratio and doing mole to mole stoichiometry. Finally, we will work on gram to gram stoichiometry and percent yield. Let's get started. The best way to get comfortable with chemical reactions is to start by just identifying the parts of the reaction. So let's take a look at this reaction right here, and let's simply identify the reactants and the products. There can be any number of reactants and there can be any number of products. The reactants are always going to be to the left of the arrow, and the products are going to be to the right of the arrow. So in this reaction here, we have two reactants, our magnesium and our hydrochloric acid. Our products are to the right of the arrow. In this case, we have two products. Our products are magnesium chloride and hydrogen gas. Another exercise for getting comfortable with chemical reactions is to take something you make regularly and turn it into a chemical reaction. So for this exercise, we are going to write a chemical reaction for making a sandwich. Now I'm going to choose one of my favorite sandwiches, which is a ham and cheese sandwich. To make a ham and cheese sandwich, I need 4 ingredients or 4 reactants. I need some sliced ham, some sliced cheese, some bread, and I like to put mayonnaise on my sandwich. Those are my reactants. You can see in this case I have 4 reactants. Now I want to switch to products. In order to do that, I want to put my arrow in. Here it is right here. And then I'm going to put my products to the right of the arrow. Well, I only have one product, even though I had 4 reactants. My product is simply my ham and cheese sandwich. This is a completely valid chemical reaction, even though you don't think about that when you're actually making a sandwich. Now that we're a little more comfortable with chemical reactions, let's start balancing chemical reactions. When we balance a chemical reaction, we want to make sure that we have the same number of atoms on the left-hand side, or the reactant side, as the right-hand side, or the product side. Remember, we cannot create or destroy atoms. Looking at my equation right now as it's written, I'm going from 1 iron atom to 2. If I didn't balance this reaction, it looks like I'm able to create an iron atom, which of course I am unable to do. I am going to use a list to keep track of my atoms. So for iron, I have 1 atom on the reactant side and 2 atoms on the product side. Simply moving left to right, I'm going to go to hydrogen. I have 2 atoms on the reactant side and I have 2 atoms on the product side. Then sulfur, let's see, I have 1 on the reactant side and 2 on the product side. And oxygen, 4 on the reactant side and 8 on the product side. Just as a reminder about multipliers, this 2 is multiplied to the oxygen as well as to the sulfur. As a general rule, hydrogens and oxygens tend to be a little squirrely, so I like to start with other atoms, but you can start wherever you want. To balance my iron atoms, I need to multiply this by 2. In order to do that, I am simply going to put a 2 in front of my iron. That 2 only changes the iron. It doesn't change any other atoms. Irons are balanced. Looking at my list, my hydrogen atoms are already balanced, so I'm going to go to my sulfur. In order to balance my sulfur, I also need to multiply by 2. Just like I did with the iron, I am going to put a 2 here in front of my sulfuric acid, or my H2SO4. Now, this does change the other atoms in that molecule. This 2 applies not only to the sulfur, but also to the hydrogen and to the oxygen, so I need to change those numbers. I now have 4 hydrogens as well as 8 oxygens. So let's go back and revisit our hydrogens because now they are not balanced. I need to multiply by 2 on the right-hand side to give me 4 hydrogen atoms, so I'm going to put a 2 right here. Now the great thing about that 2 is it only affects the hydrogen and not any other atoms. Now let's check our oxygens. Well, the great thing about that 2 in front of our sulfuric acid is it equalized our oxygens. Now I have the same number of oxygen atoms on both sides of the equation. And now I have a balanced chemical equation. Let's take a look at another example. Okay, this one looks, I know, very intimidating, but we'll just take it step by step and go through all the atoms. And then I will show you a shortcut at the end. I'm going to start just by listing out the atoms. So let's see, I have nitrogens, I have hydrogens, carbons, oxygens, magnesium, and phosphorus. And that is my complete list of atoms. Now let's count up. Nitrogens, I have 2 on the reactant side, and I have 3 on the product side. Hydrogens, 8 on the reactant side and 12 on the product side. Carbon, I have 1 and 1. Oxygen, now be careful with oxygen because you have oxygens here and oxygens here, so you're going to have to add those together. My ammonium carbonate gives me 3 oxygens and magnesium phosphate gives me 8. I have 11 oxygens. And then on the product side, ammonium phosphate gives me 4 and magnesium carbonate gives me 3, so I have 7. Now for magnesium, these should be a little bit easier. I have 3 on the reactant side and 1 on the product side. And phosphorus, 2 on the reactant side and 1 on the product side. It is easy to panic a little bit when you see these numbers and almost everything is unbalanced right now. I guess carbon is balanced. Just take it one step at a time. And just like we saw with the other problem, often you'll find that atoms will resolve when you are actually balancing different atoms. You can start wherever you want. Generally, hydrogens and oxygens tend to be more difficult. And in this case, because I have oxygen in all of my molecules, I am definitely going to save that to the very, very end. To balance my nitrogen, I am going to need to multiply by 3 on the reactant side and then, of course, by 2 on the product side. And that will give me 6 on both sides. So for my reactant side, I need a 3 over here. And my product side, I need a 2 here. This does change other atoms. So let's correct my reactant side. My hydrogens are now times 3. I have 24 of these guys. On my product side, I've multiplied by 2. And notice here my hydrogens are balanced and I didn't even try to balance hydrogens. That's fantastic. Okay, my carbons have also changed. I now have 3 on the reactant side, and I still just have 1 on the product side. Oxygens, be careful. Remember, we can't just multiply by 3 because we have oxygens in 2 places. And the same for the product side as well. For our oxygens, we now have 9 plus 8. We have 17. So I'm just going to cross through that and write 17. For my product side, I now have 8 plus 3. Again, I'm going to cross through. I have 11. My magnesiums have not changed, so I'm just going to leave those alone. And my phosphorus has changed on my product side. I now need to multiply by 2, and I have 2 phosphorus. So now nitrogens are balanced and hydrogens balanced along with them, which is great. Let's go on to carbon. Right now I have 3 on my reactant side and 1 on my product side. So let's simply multiply this by 3 to get 3. So I need to put a 3 in front here. Again, that 3 multiplies to the magnesium and the oxygen as well as the carbon. So let's change up our numbers. My magnesium is now times 3 here. And I have not changed my oxygens on my reactant side, but I have changed them on my product side. I have now 8 plus 9, which is 17. Remember how this looked so difficult at the beginning? But notice that while balancing my carbons, my oxygens balanced along with it. Is anything left unbalanced? No, everything has actually balanced out, and we did not have to go through all of these atoms. That is definitely a win. Okay, let me show you a little trick that you can use if you want, but of course, the way we just balanced is always going to work. When I look at this original equation, I notice that I have multiple polyatomic ions, and they stay intact from reactants to products. So for example, I have ammonium on my reactant side and ammonium on my product side. It doesn't break apart into nitrogen and hydrogen. The same is true with my carbonate. It stays the same, and my phosphate. So what I can do is I can treat those as one unit, or even you can think of it as one atom. So on my reactant side, I have originally 2 ammoniums, and on my product side, I have 3 ammoniums. To balance that, I do exactly what I did here. Multiply by 3 on the reactant side and 2 on the product side. That balances my ammonium polyatomic ions, which automatically balances my nitrogen and hydrogen, just like we saw when we broke it apart into atoms. Now, if I want to balance my carbonates, I have 3 carbonates on the reactant side. Again, I have this multiplier here. Originally, I only had 1, so I would have to put a 3 here. Again, just like we did when we did the atoms. That would give me 3 carbonates on my reactant side, 3 carbonates on my product side, which balances carbon as well. Now, oxygens are still probably not quite done yet. If I wanted to check my phosphates, I have 2 on the reactant side, but because I balanced my ammoniums, now I have 2 phosphates on my product side. Those are good, they're balanced. And then of course the magnesiums are already balanced because I already put my 3 here, and I have 3 magnesiums on the reactant side. So that can make it a little bit easier. You do not have to do it this way. Again, I always want you to do it the way that makes the most sense to you. Now let's start to practice a little simple stoichiometry, just doing moles to moles. Calcium reacts with water according to the following equation. Okay, great, they give us the equation. If 3.9 moles of calcium react completely, how many moles of calcium hydroxide were formed? First, we identify this as a stoichiometry problem because we were given information about a reactant, we were asked about a product. So we need to relate those with a chemical equation. If you remember our sandwich equation, this would be very similar to, say, asking how many sandwiches can you make if you have 12 pieces of bread? We know how much of our reactant we have, so we want to predict how much of our product we can make. The first thing we want to do is we want to balance our chemical equation. Now, the great thing about this equation here is it balances very easy. Our calciums are already balanced. Our hydrogens I like to keep to the end, so let's balance oxygens. To balance oxygens, I simply need a 2 here. And let's double check hydrogens. And notice that now I have 4 hydrogens on the reactant side, and I have 2 plus 2. I also have 4 on the product side. So that's it. It's done. Let's rewrite our balanced chemical equation a little neater. Here we go. And now let's start doing our actual stoichiometry. When working with difficult problems like this, if you're stuck, sometimes the best thing to do is just write down what you were given. So we were given 3.9 moles of calcium. We were asked about calcium hydroxide. So we need to move from calcium over here to calcium hydroxide. How are we going to do that? We are going to use our mole ratio. Now remember, your mole ratio comes from your balanced chemical equation, which we already have right here. So what numbers are in front of calcium and calcium hydroxide? Because we didn't write anything. Well, they're 1s. Chemists are inherently lazy, and when there's a 1, we just don't write it down. So I'm going to use this 1-to-1 mole ratio. You can see I put it right here. Now, mathematically, it doesn't matter which 1 is in the numerator and which 1 is in the denominator. We're both multiplying and dividing by 1, which isn't going to change anything. But this is a great time to practice our units when the math does not matter. We have moles of calcium that we started with. We need to make sure that that cancels. So you notice I put my moles of calcium in the denominator so that we get cancellation here, which means I am left with moles of calcium hydroxide. This is exactly what my problem asked for. You've heard me say it before, and you'll hear me say it many times again. Let your units lead you. The math part of this equation is easy. We have 3.9 times 1 divided by 1. So we are going to get 3.9 moles of calcium hydroxide. The real purpose of this exercise is to first balance your equation again, and second of all, to make sure you can get your units in the right place without having the math complicate things too much. Let's stick with this same chemical equation, but ask a different question. So now what we want to know is if 0.050 moles of hydrogen were formed, how many moles of water reacted? So in this case, we are starting with a product, our hydrogen, and we're asking about a reactant, water. We do this problem the exact same way. We are going to start with what we were given, our 0.05 moles of hydrogen. To move to a new molecule or a new atom, we are going to use our mole ratio. Now in this case, our hydrogen does have a 1 in front of it, but our water has a 2, so now we need to take the math into account a little bit more. I set up my mole ratio the same way. I have been given moles of hydrogen. That is what I want to make sure cancels. So here is my mole ratio. You can see that I put my moles of hydrogen in the denominator there, so I get cancellation. I am left with moles of water, which is exactly what the problem asked me for. And now I have just a little bit of math. So I'm going to take my 0.05, I'm going to multiply by 2, and then divide by 1, which of course doesn't really change anything. And I have used 0.1 moles of water. I wish I could say we'll always stay in moles, but of course, no balance in the world is going to measure out moles. They're all going to measure out some kind of mass, usually grams. So we need to be able to take, say, grams of a reactant and predict grams of product. Let's take a look at our next equation. Our equation says ammonia is formed when hydrogen and nitrogen gas react under pressure and heat. And they give us the chemical equation. That's great. And then it asks if 12 grams of hydrogen react, how many grams of ammonia are formed? How do I know this is a stoichiometry problem? I'm given information about hydrogen, which is a reactant, and I'm asked about ammonia, which is a product. I need to relate those two compounds by a chemical equation. Is our chemical equation balanced? No, of course it's not balanced. We're going to have to balance it first. When working any chemistry problem, always assume your equation is not balanced. It is awful to do all this work in a problem and realize that you haven't balanced your chemical equation. I know from experience. Just because I don't like to balance hydrogen first, I'm going to balance my nitrogen first. So I have 2 nitrogens on my reactant side and only 1 on my product side. Let's balance that out with a 2 right here. Now I'm going to have to bite the bullet and balance my hydrogens. I have 2 on my reactant side and I have 6 on my product side. This isn't quite so bad. A 3 here ought to do it. Let's rewrite that a little neater. Here we go. And now let's start my stoichiometry. I was given 12 grams of hydrogen. I was asked about ammonia. So I know at some point I'm going to have to use my mole ratio to switch between hydrogen and ammonia. Unfortunately, grams do not allow this switch to occur. So first I need to convert grams to mole. Remember, when you're switching between reactants and products or products to reactants, you are using a mole ratio, not a gram ratio. So you always want to make sure any grams are converted into moles. Using my molar mass right here, my grams of hydrogen cancel. Now I have moles of hydrogen. Plugging into my calculator, 5.95 moles of hydrogen. Now that I have moles, I can use my mole ratio. So here again, I'm just rewriting my 5.95 moles of hydrogen. I'm going to use my mole ratio to convert between hydrogen and ammonia. Here is my mole ratio. Notice my hydrogen cancels, so I'm left with moles of ammonia. Putting this into my calculator, I get 3.97 moles of ammonia. Okay, this is fantastic. The problem asked me about ammonia, and now I have ammonia. But there is one more wrinkle. The problem asked me for grams of ammonia, and right now I have moles of ammonia. So I need one more step. Taking my 3.97 moles of ammonia, I'm going to use my molar mass right here to convert from moles of ammonia to grams of ammonia, and I get 67.6 grams of ammonia. And now I have finally answered my question. Once you get more comfortable with these problems, do not feel like you have to break this apart into 3 separate steps. You can also put these steps together, just making sure your units cancel. Let me show you how this works. Here's my 12 grams of hydrogen. My first step was to convert grams to moles. Notice the grams of hydrogen cancel. I'm left with my moles of hydrogen. My second step, I took my moles of hydrogen and converted to moles of ammonia using my mole ratio. Here's my mole ratio. Notice my moles of hydrogen cancel. My last step was to take my moles of ammonia, use the molar mass to convert to grams of ammonia. So now my moles of ammonia cancel, and I'm left with grams of ammonia. So hopefully you can see here how I have canceled all of my units until I'm only left with grams of ammonia, and then I can plug this whole big thing into my calculator and get an answer a little more quickly. And you can see here I get the same answer, the 67.6 grams of ammonia. As always, use whichever method makes the most sense to you. Let's do one more gram to gram problem. So we are going to keep the same chemical equation. That's great. We don't have to worry about balancing again. And this time the problem asks if 75.5 grams of nitrogen react, how many grams of hydrogen are needed? I know it's stoichiometry because I have been given grams of nitrogen. I've been asked about grams of hydrogen. Those are 2 different molecules. I need to relate them by a chemical equation. Now notice in this case both hydrogen and nitrogen are reactants. And you might think, wait, this isn't stoichiometry because I haven't gone either from reactants to products or products to reactants. But no, this is also stoichiometry even when you're staying within reactants, because we will relate the hydrogen and the nitrogen by the mole ratio. Speaking of mole ratios, we were given 75.5 grams of nitrogen, so our first step is going to be to convert to moles so we can use that mole ratio. So using the molar mass of nitrogen, my grams of nitrogen cancel. I'm left with moles of nitrogen, and I get 2.69 moles of nitrogen. Now that I have moles of nitrogen, I can use my mole ratio. So just rewriting my moles of nitrogen, here is my mole ratio. Again, I want to make sure my moles of nitrogen cancel, and I'm left with moles of hydrogen. Putting this in my calculator, I get 0.898 moles of hydrogen. Unfortunately, the problem asked me about grams of hydrogen, so I have one more step. Rewriting my moles of hydrogen, I simply use the molar mass to convert to grams. So being careful that my moles of hydrogen cancel and I'm left with grams of hydrogen, I get 1.81 grams of hydrogen. Just like before, we can put this in one long equation. So starting with my 75.5 grams of nitrogen, my first step was to convert to moles. So here's my molar mass, again making sure that my grams of nitrogen cancel. Next, I used my mole ratio to convert from moles of nitrogen to moles of hydrogen. So again, I made sure that my moles of nitrogen canceled. Now I have moles of hydrogen, but for my final step, I wanted to convert to grams of hydrogen. So here's the molar mass. My moles of hydrogen cancel. I'm left with grams of hydrogen. And now I can plug this longer equation into my calculator, and I still get my 1.81 grams of hydrogen. Next, let's talk about percent yield. In an ideal world, a chemical reaction would always give 100%, and we wouldn't actually have to do this. But unfortunately, we do not live in an ideal world. You have probably noticed this just in everyday life. So if we, again, go back to our sandwich example, let's say we knew that we had 10 slices of bread. We expected to make 5 sandwiches, but when we were using the bread, we noticed one of those middle slices had a big hole in it. Well, suddenly we can't make as many sandwiches as we thought because one of our slices of bread was not functional. The same thing happens in chemical reactions. What we expect to get is not always what we actually get. Let's read our problem. We have a new chemical reaction. And it looks like they balanced it for us. Let's see, 4, 4, 2, and 2. Yes, they balanced it for us. That's great. That's one step we do not have to do. The problem reads, if 75 grams of oxygen reacts, only 355 grams of potassium oxide is formed. So they want to know what is the percent yield of the reaction. Let's start with what we were given. We were given 75 grams of oxygen. Our first step is to convert to moles of oxygen because we need to use our mole ratio. So using the molar mass of oxygen and making sure that my grams cancel, I now have moles of oxygen. Now to convert between oxygen and potassium oxide, I need my mole ratio. Again, this is where it's great that my chemical equation is already balanced. Here is my mole ratio. My moles of oxygen cancel, and now I have moles of potassium oxide. However, the problem gave me grams of potassium oxide that were actually formed, so I need one more step. I need to convert the moles of potassium oxide into grams of potassium oxide. So using the molar mass, here my moles of potassium oxide cancel, and I get 441.5 grams of potassium oxide. This is how many grams of product I should get simply based on the math. This is my theoretical yield. Again, if you know you have 10 slices of bread, you expect to make 5 sandwiches. Obviously, this reaction did not make the expected amount. We expected 441.5 grams, but our problem told us that we only got 355 grams. So what is our percent yield? Let's get the equation for percent yield up. Here it is. It is our actual yield over our theoretical yield. We just calculated our theoretical yield. This is what we get when we do our stoichiometry. Our actual yield is what actually happened. Our problem told us we only got 355 grams in the actual yield, but our stoichiometry predicted 441.5 grams. So I simply divide, multiply by 100%, and I get a percent yield of 80.4%, which is actually not too bad. Let's do one more percent yield problem. This time they give us the percent yield. So the percent yield of the following reaction is 35%. And they give us a chemical equation and it's already balanced. That's fantastic. If you need to form 20 grams of sulfur trioxide, how many grams of oxygen should you use? So this is very much, if we go back to our sandwich example, you know you need to make 5 sandwiches, but you also know that maybe half of your bread is not going to be usable. So you're trying to figure out how many slices of bread you should get to make sure that you can make all of your sandwiches. Of course, we know we need to do stoichiometry because we are given grams of sulfur trioxide and asked about oxygen. So at some point, we are going to have to use our mole ratio from our balanced chemical equation. Let's get our equation for percent yield up. Here it is. Now the problem gave us our percent yield at 35%, so I'm going to put that in. Let's see what else we can fill in. We don't know our theoretical yield yet. We haven't done any stoichiometry, but we do know our actual yield. We need to actually form 20 grams of sulfur trioxide. So that is our actual yield. So being able to put in the percent yield as well as the actual yield, we can calculate our theoretical yield. Our theoretical yield is going to be 57.1 grams of sulfur trioxide. That is actually a huge chunk of the problem already done. Now for our stoichiometry. We have grams of sulfur trioxide, but we need grams of oxygen. So we need to convert using our mole ratio between sulfur trioxide and oxygen. So rewriting my 57.1 grams of sulfur trioxide. Because we're doing a mole ratio, we need to first convert to moles. So using my molar mass, making sure my grams of sulfur trioxide cancel. Now I've got moles of sulfur trioxide. Once I'm in moles, I can use my mole ratio from my balanced chemical equation, and thankfully they gave us a balanced chemical equation. And my moles of sulfur trioxide cancel, and I'm left with moles of oxygen. But of course, we need to know grams of oxygen, so we have one more step. Using the molar mass of oxygen, this time we make sure our moles of oxygen cancel, and we're left with grams of oxygen. Now putting all this into the calculator, we get 11.4 grams of oxygen. This is huge in chemical industry because if you have a reaction that only goes to 35%, it's very important for you to know how much of each of your reactants you need to form a certain amount of products. So these kind of calculations are used every day all around the world. And now you know how to do it too. I know stoichiometry can be confusing and overwhelming, especially the first time that you've seen it. The best advice I can give is just practice, practice, practice. So I hope you found working these problems with me helpful, and thanks so much for watching.